blackboard here. So we did the first two problems in the last class, and I'm a little bit more organized this time. So I actually have the test on my iPad. Also, one more thing is I have the note cards from the last two tests. And if you're a primarily Zoom person, I have your tests as well. So if you want to pick that stuff up, I will be in my office today from 2:30 p.m. to 5 p.m. Right after this class is over, for those of you in the room, I also have piles here, including the tests. So if you haven't picked it up yet, feel free to do so. All right. So we did problems 1 and 2 last time. So let's do problem 3. And this is, your time to shout out questions and everything. This is like a review for the final. So if you don't understand something, speak up now or forever hold your peace. No, you can ask later too, but speak up if you have questions. So let's look at this particular problem. Let's do blue because that's a less scary color. What is the code? Does anyone remember the code? 4819. 48, is that right? Yeah, 4819. Okay, so in this particular problem, it says that there is a sled of mass 5 kilograms. It is pulled across a horizontal frictionless surface with a force of magnitude 30 newtons, which makes an angle of 40 degrees above this horizontal surface. So the first thing I will do is just draw a picture, a cartoon picture, just to tell myself like what's going on physically in this problem. Maybe I'll do the figures in black here. So here is a horizontal surface. Here is a sled being pulled across it on this horizontal surface. And we are told that someone is applying a force of 30 newtons, which makes an angle of 40 degrees above this horizontal surface. So that means someone is pulling on this like so with some force F that is some angle theta, which in this case is 40 degrees above the surface. Now, the first thing that I want to point out is that this, what I've drawn here, is not a free body diagram. It is simply a cartoon representation of what is physically going on. And once I have this picture in my mind, I will then do a more careful analysis to draw a free body diagram. So the first thing I want to do is let's figure out what is this question asking. So this is a situation here. And the question is, what is the magnitude of the normal force that this ground exerts on the sled as this thing is moving to the right? Okay, so we want to figure out what is the normal force in this situation. Any questions about that? The concept that we're going to use here is Newton's second law. Newton's second law says that the net force on an object is equal to its mass times acceleration. And we can apply that either along the x-axis, and we can also apply that along the y-axis. So we know, for example, right away that along the y-axis, the net force must be 0 because the sled is only moving along the horizontal surface. It's not at all moving up or down, which means its acceleration in the vertical direction is exactly 0. That means if I look at the components of all the forces in the vertical direction, they must add up to 0. And one of those forces is the normal force. So in all these types of problems, these chapter 4 types of problems, the idea is you're using Newton's second law. You can apply it in the x direction or in the y direction. And you want to draw a free body diagram that helps you write out Newton's second law, and then you will solve for whatever variable is given to you. So what I'm going to do now is I'm going to draw a free body diagram. And I want to emphasize the meaning here of a free body diagram. So the first thing you have to do in drawing a free body diagram is that you have to free the body from its surroundings. So don't draw the ground, don't draw a person pulling on it. You're drawing a free body diagram for the sled. So you can represent the sled as either a point or a box or something like that. In this case, let me just go ahead and represent it as a box. So here is the sled. Again, I'm just drawing it. That's all I'm doing. I'm not drawing the floor, the person, or anything like that, pulling on this. That is the free body. I've freed the body, and now all I'm going to do is draw all the forces that are acting on it. Once you get experience with this, you can draw it in such a way that you immediately draw all the forces resolved along X or Y. I'm going to do it in 2 steps, where we will first physically identify all the forces, and then I will resolve it into X and Y components. So let me go ahead and say here, let's call the horizontal direction to the right the positive x-axis, and this my positive y-axis. That's my coordinate system. And what are the forces acting on this sled? Well, one is we know that there is this force F that is being that's going in this direction, like so, at some angle theta. We know that there is the force of gravity downwards. So the force of the weight of the object, that'll be mg. Right? Another thing that I want to emphasize here is a lot of people in their tests, when they draw the force for gravity, what they will do is they will put the arrow here and then they will just say G like that. This is incorrect. G is not a force, G is acceleration, right? The force is the force of gravity, which is the weight, and near the surface of the earth, that force is m times g. So in this picture, you're only drawing forces. You're not drawing acceleration vectors or anything like that. It's a free body diagram. So the weight is mg. Any questions on that? What else is there? There is the normal force acting straight up, which is this ground here is going to be pushing up on this sled. And those are the 3 forces. Now, as this sled is moving to the right, there may be a force of friction between the ground and the sled, but here we are told that it is a horizontal frictionless surface. So there is no friction in this example. If there was, then I would probably draw a force of friction here to the left, but there isn't. Also keep in mind that I put arrows on all these forces. Some of you would kind of drop the arrows, and that would just give me OCD. It's just you would draw something like that, like that's the force F. But keep in mind that force is a vector. So what you want to do is put an arrow that's telling you which way it's pointed. Any questions about that? Now, what I've done in this is a legitimate free body diagram, except the problem is, in order to help me solve the problem, I have not resolved all the forces along X or Y. So if I look at the force of gravity, that's good because that is exactly along the negative Y-axis. The normal force here is also exactly along the Y-axis. That's good. But there's this force F that's at a weird angle. It has some component along X and it has some component along Y. And so what I want to do is resolve that vector into its X and Y components, which basically means, and I'll go ahead and draw this here in red, that what you want to do is take this force F and write it as a sum of 2 other vectors, one that points completely along X and another that points completely along Y, right? Where they make a 90-degree angle. That's what it means to resolve a force into its components. That is, you're writing it as a vector that points along x and along y. And we are told that this angle here, remember, is theta, right? This angle here is theta. So that's your angle theta. So now you have a nice right triangle here, where in some sense, what I'll do is I'll move this f over here. The f here is essentially the hypotenuse of that triangle, right? It's the length of that force vector pointing in some other direction. And what is going to be this horizontal component? Just by trigonometry, it'll be f cosine theta here, and then this will be f sine theta going upwards. Those are the lengths of the two sides of the triangle using trigonometry. Any questions on that? So now what I'm going to do is I'm going to draw the free body diagram where it is completely resolved, where all the forces are pointing completely along x or y axis. So here's my x axis again, my y axis positive y upwards. So again, I will have here my force of the weight mg, not g, but m times g. I have my normal force upwards. And then I am no longer going to draw this force F, but rather this F is equal to this F cosine theta along X plus F sine theta along Y. So I'll just replace it by the sum of those two vectors, which means now I will have one force that points to the left, which is points to the right, which is F cosine theta like so. And I will have another vector that points upward like so, or maybe I'll draw it, let me draw it as a separate vector here. Let me just move this thing over a bit, like so. And then here I can draw another force. Maybe it's something like this, and this is F sine theta. So now this force F, this force F is now gone, and I have replaced it with F cosine theta plus F sine theta, like so. Now all the forces in this free body diagram are pointing either along X or along Y. Any questions on that? So now that I have a free body diagram, I will now apply Newton's second law. Newton's second law. Which says, it's a vector equation that says that the net force on an object is equal to its mass times acceleration, which is a vector equation, meaning that the sum of all the forces along the x direction must equal the mass times acceleration, and the sum of all the forces along the y-axis must equal the mass times acceleration along the y-axis. Right, so these are the two vector components of these equations. And this picture here, this free body diagram, is going to help me write these two equations out. I literally look at this picture to figure out how to write these equations. The thing we're trying to find is the normal force here. We're trying to find this normal force. What I'll do is let me look at all the sum of the forces along the y-axis. And what do we know about the acceleration in the y direction? We know that this is equal to 0, since there is no acceleration along the y-axis. The sled is only moving on the surface. It's not moving up and down, so it has no acceleration along the y direction, which means that the sum of the forces along the y-axis is 0. And now I will just look at this picture here. There's a force N pointing in the positive y direction. There's F sine theta also in the positive y direction. And then there's the weight mg in the negative y direction. So I'll go minus mg, and that is equal to 0. I could, if I were to, in this particular problem, I'm only interested in solving the normal force, and you can see that I can go ahead and solve this immediately to get the normal force. I know F is 30 newtons, theta is 40 degrees, mass is 5, G is 9.8. So I already have everything I need here to solve for the normal force. I don't even need this equation here on the left. So what I'll get here is I will say, therefore, N is equal to mg minus F sine theta. Notice that this normal force is not equal to the weight. It's a little bit less than the weight because this person that's pulling with the rope here is helping the normal force along a little bit, right? It's kind of lifting the sled a little bit off the ground. And so therefore this normal force doesn't have to support the entire weight, but the weight minus whatever help it's getting from the person pulling on it. And now you can go ahead and plug in numbers, and let me go ahead and make this a top hat question. So here's our top hat question 1. Okay, any questions on this so far? Let me go here. So this is that problem here. Find the magnitude of the normal force acting on the sled. Let me start it, and so the question is open, and I can go back here and display this while you're answering that. Any questions from anyone about this? Let me add a timer here of a minute and a half. Oh, sorry. I forgot to turn my camera on to the Zoom people. My apologies. Let's see what we got. 30 seconds. For the person in the chat, I guess try just rebooting. And if it continues to give you a problem, then you can, yeah, that's right. You can use the browser version too. Yeah, if you're on a phone, maybe try to move to a laptop, something like that. All right, let's see what we got. Yes, so it looks like most of you got it. And the correct answer here, if I now plug in numbers, right, we know that M here is 5 kilograms. We know that G is 9.80 meters per second squared. We know that F is 30 newtons, and we know that theta is 40 degrees. So if I take all this information and plug it in here, you get that N is 29.7 newtons. So that is the correct answer. Any questions on that? Another question that could have been asked in this problem is, it could have been asked, what is the acceleration of this sled as it moves along? How would you do that? Well, in that case, they're asking you for this AX. They're asking you for this acceleration of the sled. The AY is 0 because it doesn't move in the vertical direction. So if I look at this picture here, I could write down my Newton's second law. Along the x-axis, the only force acting there is F cosine theta. There's nothing else acting here. So therefore, the sum of these forces along the x will just be F cosine theta, and that is equal to m times ax. And then you could, for example, solve for ax, and that is equal to F cosine theta divided by m, and you can plug in numbers, and you will get some particular number. That could have been like a part B for this question, for instance. All right. Any questions on that? And again, the thing I want to emphasize here is, this is this stuff right here is what it looks like to show your work, to draw diagrams appropriately, to write down symbolic equations. This number here, 29.7, is literally the least interesting thing in the entire problem. But if you show this kind of work, I can give you lots of partial credit, even if this last number here is not correct. All right, let's look at this one. Here, we are told that a block of mass 5 kilograms here is suspended by a string of tension T from the ceiling of an elevator. The elevator accelerates upward with an acceleration of 2 meters per second squared. So this thing is accelerating upward, the whole elevator, with A equaling 2 meters per second squared. What is the magnitude of the tension in the string? Again, let me emphasize that this picture here is not a free body diagram. It's a cartoon of what is physically happening. And we want to then translate that into a free body diagram just for this mass M, so that we can figure out what is this force of tension that is acting on it. Another tendency that some students had is that you would tend to draw the forces on this picture itself. So some of you would just kind of go here and then put an mg here and then a t there or something like that. Don't do that. You want to draw a free body diagram separate from the cartoon. Okay, so make a separate picture. Don't draw it on this thing because it's confusing because you don't know that part of it is a cartoon, part of it is a free body diagram. So again, what I will do is, our goal here is to find the tension, and I'm going to draw a free body diagram for this mass M. I'm going to draw my X and Y axes. That's my positive X, that's my positive Y as my convention. What are the forces acting on this particular mass here? There's the force of gravity down. So there's mg. And again, it's not g, it's m times g. It's the weight, that's the force. G is the acceleration due to gravity, but this is just the force, mg. And on this mass, the only other force acting on it is this tension. There's a tension from the rope. So therefore, all you get is a force of tension upward. That's it. These are the only forces acting on it. Some people were confused by this acceleration that's given here. This is not a force. This is just telling you that this is the acceleration of the elevator. And since this mass is tied by a string to the elevator, we know that this acceleration of 2 meters per second squared is the acceleration of this mass as well as it goes upwards along with the elevator. But that is not a force. So I will never draw this A equaling 2 meters per second squared anywhere here in the free body diagram. The free body diagram is only reserved for drawing forces, not acceleration. So now what I will do is I will now apply again Newton's second law. Newton's second law. And in this case, we only have one direction, the vertical direction. There's nothing really happening in the x direction. And the Newton's second law will say that the sum of the forces along the y-axis in this case is going to equal the mass times the acceleration along the y-axis, right? Which in this case is equal to m times a. That is your ay here is equal to A, which is 2 meters per second squared. So this is where the information about the fact that the elevator is accelerating upward, it appears on the right side of this Newton's second law. So the left side here, the sum of the forces, that comes from the free body diagram. The right side is what is the acceleration of this mass m. The acceleration of this mass m is the same as that of the elevator because it's tied to the elevator. So therefore, this ay is equal to this a, which is 2 meters per second squared. So now I can go ahead and say, therefore, if I now add up the forces along the y-axis, there's a force of tension upward in the positive y direction. There's the force of gravity downward in the negative y direction. So I'll go minus mg, and that is going to equal m times a. This acceleration a is plus 2 meters per second squared, and it's pointing in the positive y direction. So that's why ay here is equal to plus a, right? It's plus 2 meters per second squared. And the thing that we want to solve for is the tension. So the tension is mg plus ma. So notice that if this elevator were at rest, it was not accelerating, it was just at rest, this tension here would just be equal to mg. The a here would be 0. The tension would just support the weight. But now in this situation, the tension has to be greater because it doesn't have to just support the weight. It has to also accelerate the thing. So it has to overcome the weight and give an extra force so that the thing is accelerating upward with 2 meters per second squared. And so therefore, you get the tension in this way. So let me make this a top hat question and see, so figure out from the numbers here, what is the value of the tension in this case? Any questions on this? So this is it's a simple problem, but it's conceptually an interesting problem, specifically that when you're drawing the free body diagram, you only draw forces. You do not draw acceleration vectors anywhere on the free body diagram. All the acceleration information is on the right side. Any questions on that? All right, so let's go to top hat. Let me add a timer of 1 minute. Oh, can I go back to the problem? Yes. Let me just add another minute. Twenty seconds. All right, let's see what we got. Yay. So that is indeed correct. The correct answer is, I believe, 59 newtons. So if you plug in the numbers here, you get that the tension is 59 newtons. So here M was 5 kilograms. G is again 9.8. And A is 2 meters per second squared. So all of this goes in there to give you your final answer of that. Notice another thing I want to point out is that in these two problems, I have used exactly the same concepts. I have drawn a free body diagram, use Newton's second law, solve for the normal force, solve for the tension. So some of your note cards I've seen, they are just full of all kinds of random equations. What you're doing there is you're trying to write down, in some sense, implicitly, you're writing down a solution to every problem in the world. And then you end up with this big manifesto of a note card. But all you really need is Newton's second law. That's it. This one equation with understanding helps you solve both of these problems in exactly the same way. It's the same strategy applied in a different situation. So, any questions on that? All right, and then there's this fifth problem here, which is again, the same concept again. It's going to be draw a free body diagram, write down Newton's second law. The only complication here is that things are at a bit of an angle, and so the geometry can be, or the trigonometry involved is a little bit more non-trivial than in the other problems. But again, the concept is the same. It's F net equals MA, F equals MA, Newton's second law, draw a free body diagram, write down the equations, and solve for whatever variable is being asked. So here, let's do part A. Part A, it is asking to draw a free body diagram for the crate. So there's this crate here that is being pulled up by some force along this incline, which does have friction. So now it's not frictionless. It has a coefficient of kinetic friction, mu sub k equals 0.350. So the first part is simply saying draw a free body diagram of this object. And then a sub question there is, once you draw that free body diagram, resolve all the forces in that free body diagram into components either parallel or perpendicular to the diagram, and show them on the free body diagram. So first, let me just do the following. What I will do is I will pick, just for illustration here, and again, don't draw the forces on this picture, but make a separate picture down here, free the body from its surroundings. But just to give you a little bit of orientation, what I will be doing is I will pick my x-axis along the incline and my y-axis perpendicular to the incline in this way. So in these inclined plane problems, it just becomes useful to pick your x-axis along the incline and your y-axis perpendicular to the incline. You don't have to do it. You could pick it horizontal, but then you complicate your trigonometry for some other things. And so a good strategy is to kind of pick your forces in this your axes in this particular way. So now what I'm going to do is let me draw this free body of that crate as a point. Let me just make this as a point here. So that's my mass M. So this crate here is now represented by this particular point. And just because things are on a tilted plane, and I want to draw my forces relative to these X and Y axes, I'm going to go ahead here with some dotted lines, just indicate that this is kind of like my X-axis. That's the surface of the incline. And then this is like the perpendicular direction to that incline. So this is like your X-axis here. This is your Y-axis. So again, this is your X and that's your positive y, like so. So all I've done is drawn the picture of the mass m as a dot, and then shown what my axes are, and now I can draw my forces in relation to these axes. So the first thing, there's the force of gravity. Its weight is always going straight down towards the earth. So that means I can go ahead here and draw my force mg straight down. Right? Gravity doesn't care that you're sitting on an inclined plane. It's always pulling you towards the surface of the earth. So that's mg. Then there's this force F, which is precisely along the positive x-axis up the incline. So that's there. Then there is a normal force. There's a contact force between the surface and the M. And again, normal forces, they're normal. They're always perpendicular to the surface, which means that the normal force here will be exactly along the positive y-axis, perpendicular to the incline. And then we are also told that as this crate slides up, there is a force of kinetic friction between here and here. Well, the force of kinetic friction is always opposing the motion. It's always going in the opposite direction of the displacement, which means that your force of kinetic friction will be downwards since the crate is being pulled upwards, as we're told in the problem. There is a force of kinetic friction here, F sub k, pointing in the negative x direction. Any questions on that? Any other forces in this problem? I think that's it. There are no other forces acting on the problem. It's gravity down, a force F up, normal force, force of kinetic friction. So again, you can see in this picture, we've answered the first part of this A. We have drawn a free body diagram with all the forces identified. The second part says resolve all the forces into components either parallel or perpendicular to the diagram and show them on this free body diagram. So we want to resolve all these forces either along x or along y. And we see that F is perfectly along the x. The force of kinetic friction, F sub k, is perfectly along the negative x. Normal is perfectly along the y. It's only this force of gravity that is off kilter. It's not along x or y. So now I want to break it up into components that point along x or y. And again, what I will do is I will simply write this vector as a sum of a vector along the y-axis, in this case, the negative y-axis, and then something that's parallel to the x-axis, in this case, the negative x-axis, like this, where this angle here will now be 90 degrees. And what I'm going to do is move this mg here, and just for illustration, I will write it as mg like so. So that you see now you have a right triangle whose hypotenuse is mg. Right, this is the hypotenuse, the side that is opposite the 90-degree angle. And this angle theta here is precisely this angle theta here. And you can see that because just imagine, right, you take the incline when it's horizontal and you start to rotate it by some angle theta, then what's going to happen is essentially it's like you're starting out like this where it's horizontal, and then you are rotating by some angle theta like this and by some angle theta like this. That's how you get from a horizontal surface to an incline. And so this theta here is exactly this theta here. So let me go ahead and, for clarity, get rid of those last few things that I drew. All right. So now what I'll do is I'll now draw a separate diagram where all of these things are completely resolved. So there's my x. This is my y, x, x, y. here's F, here's the normal force, here's the force of kinetic friction, F sub K. And then from trigonometry, we know that this side here is mg cosine theta, and this opposite side here from the theta is mg sine theta. Any questions on that? Which means that I am now going to replace this mg with this plus this. So this mg cosine theta here is now going to be along the negative y-axis. So that's my mg cosine theta. And then I also have this mg sine theta pointing in the negative x-axis. So I will now go ahead here and draw another force, which is mg sine theta, like so. Any questions on that? So this is the solution to the second part of this part A. Question. All right. So let's. Oh, somebody just waking up on Zoom. So let's do part B real quick. What is the normal force? B is, what is the normal force? Well, now that you have this diagram here, it's real simple. I will use Newton's second law. Newton's second law says that the sum of the forces along the y-axis must add up to 0 because there is no acceleration in this direction. The crate is only moving along the incline. So therefore, the acceleration along here has to be 0. So therefore, very quickly, I can write sum of the forces along y has to equal 0 because it has 0 acceleration. Therefore, n minus mg cosine theta is equal to 0. Therefore, n is equal to mg cosine theta. So let me just go ahead and make that a top hat question quickly. So in that picture, let's go ahead and compute what is the normal force. And then we can quickly do the friction one as well. $18 seconds. All right, and that is indeed correct. That is, you get, I believe, n is about 46 newtons. Very quickly, what is the force of kinetic friction? Now, here is another concept that comes into play, which is that we built a model. Remember that the force of kinetic friction is given by the coefficient of kinetic friction times the normal force. So this is a new concept. It doesn't come from Newton's second law. This was the model for friction that we developed. And so now all I'll do is here go 0.350 times 46 newtons, and that gives you 16.1 newtons. And let me very quickly just do part C as well. Part C says, what is the acceleration of this crate as it goes up the incline? Well, it's real simple. Once you have this picture, all you have to do is say that the sum of the forces along the x direction is mass times the acceleration along the x direction. The sum of the forces is, just by reading off this picture, it is simply F minus F sub k minus mg sine theta is equal to mass times the acceleration. And therefore, the acceleration is F minus F sub k minus mg sine theta divided by m. And you now know all of these things. You just figured out the force of kinetic friction here. You know that F is given to you. It's 80 newtons. And you know the mass and you know theta. So you can figure out the acceleration. And if you do that, I believe you get 9.43 meters per second squared. All right, so stay calm and all the best to you in the rest of your pursuits, and come say hello 5 years from now. Let me know what you're doing. Let me stop the recording.